Uttarakhand, and he is the expert member of NSM group on application development, National Supercomputing Mission Area, Geophysics and Oil Exploration. He has been into many other committees including Board of Studies for many universities. Satish is currently acting as Chief Warden for New Hostel Vikrant Ganj, NHVK, and he is also member of PAPC, FIC exam, and he was the member of IAPC. It's our honor, and his research interests include ground computing and mobile computing and mobile security. So it's our honor that he is with us today. So I invite you to this ICIT 2022 session, sir, and over to you.
Yeah, thank you so much for the introduction. Let me share the slides.
Please don't make the noise. YouTube then ತುಂಬಾ ತಲೆ ಕೆಡಿಸ್ಕೊಳಕ್ಕೆ ನಾನು ಇಲ್ಲೇ ಜಾಯಿನ್ 866 06 06
Can you please confirm if you are able to see my PPT?
Nitin. Yes sir, it's loading sir, it's loading. Yeah, it's visible sir.
Okay, thank you so much.
Yeah, you can go ahead.
Okay, so good morning everyone. First of all, I would like to thank Professor Nagatna and Professor Yoga for inviting me here for this talk, and of course the entire faculty of the department, all the organizers and management and principal director of the institution. And congratulations to all of you for joining this conference, and best wishes for your future. So, given this introduction, let me straight away jump into the topic. So, I plan to take a session on how mobile malware detection models can be designed in the specific context of Android mobiles. And I'll try to highlight some of the research outcomes of our research, from our laboratory, for which a lot of students' contribution is there. And I'll try to present all that work stream. So, basically, when we are talking about mobile malware, so obviously most of the times we talk about Android phones only, just because the majority of the phones are Android phones. And just in a couple of minutes, I show you that how much penetration of these mobile phones were there from the context of Android. So, there is a lot of scope for research in this direction, as long as Android is there, as long as mobile phones are there. You are having you can take a lot of research in this direction as well in the future. Yeah, so basically this talk focuses on 10-15 minutes of introduction to highlight why mobile phones, why security, why Android. So these aspects we will try to consider in the introduction part. We will try to understand the importance of this, the topic. And of late, I will try to discuss a couple of research directions which we have taken up in our research. And typically, the Android mobile malware detection models are classified into three types: static detection models, dynamic detection models, and hybrid detection models. So we will, I will try to highlight one model at least for each case, so that you understand the difference and importance of all these models. And also, if your interest is in a specific domain, then probably you can choose that direction and you can take a research in that direction. So with that motive, I will be discussing uh, three different types of models. I'll be at least two for sure. One model I'll be giving you the general idea. Okay. And finally, I will conclude the session with some possible directions for the research. Okay. So if you see the statistics, there is a huge surge in increase in the number of mobile phones that are entering into the market, as well as the people who are using the internet through mobile phones is also drastically increasing. And if you see the statistics here, so the mobile phones market share is almost like 52 percentage compared to the desktop systems. And the internet traffic, this is a very important point. The internet traffic is like increasing like anything. It's 60 percentage of the traffic is just through your mobile phones. And the one of the crux of crux point of attackers is that the weakness of this security issues is that, so in the most of the attacks happen through internet sources. So this, as the surge of this internet access increases, the possibility of attacks also increase. So we should also focus on this direction. Yeah. And there are many other reasons why. Yes, hello. Yeah. Am I audible to everyone?
Yes, sir, you can. Yes, sir. Yes, sir. Please carry on.
Okay. Thank you so much. Okay. So here, so why there is a surge in mobile phones or mobile devices? It is because mobile devices provide ease of access to every application and on your fingertips. And apart from that, it provides a lot of features. The most important point is it provides a lot of features, including your simple internet browsing to your social networking, online gaming, online shopping, several other reasons why these mobile phones are becoming so important these days. And the size of the mobile devices that are occupying in the world are uh, almost like, reaching to the size of your I mean, it is almost crossed the size of your population, and the numbers are increasing day by day. Yeah. And when you consider a specific operating system that dominates the internet, like mobile phones usage, if you see here the graph, you notice that before 2012, people were using like the basic phones, or probably the Symbian operating system based phones, which were allowing hardly GPRS based internet connection. And the major purpose of the phones was the calling, messages, SMS, and hardly any other thing, probably with GPRS, little bit of internet connectivity. As the smartphones came into the picture, then they become touchscreen and accessing to the applications, services, have become much simpler and easier. At the same time, iOS operating system, um, like Android operating system, Symbian operating system, there were many other operating systems that were competing at that period before 2012 and odd. So at that time, the existence of the phones was itself is a big thing. But after 2012, there is a huge surge in the adoption of mobile phones, and they have become much cheaper. And during that time, the quality of services also increased. Like for example, um, they have become touch screen. They have become internet enabled. Internet services quality also increased. For several reasons, people started jumping into using of more of smartphones. Okay. And during the same period, almost the same period, Android operating system was introduced. So for some duration of time, there were other operating systems which were popular at that time. So they were occupying the big market at that time. So they just gone down, and iOS operating system almost stable in its occupancy in the market, but the Android operating system slightly around 2012 entered, and it took a big surge in the market. And that is the reason why, why Android, that we'll see slightly in the next slide. But typically, the interest of the users, became important towards the Android operating systems compared to uh, compared to uh, other operating systems. And iOS market share was fixed almost, and it is consistent for over years. Okay. So what the attackers can do towards these mobile phones, may it be Android, may it be your iOS, or may it be any other operating system. Okay. So the reason is, if you notice the what is called mobile phone systems, then you can notice that here. Okay, so sorry for that. Yeah, so you can notice that on your phone you can essentially store. I mean, you take your photos, videos, you store a lot of your personal information. Particularly, there would be a lot of confidential information, right? Which might include your banking credentials. And if you just take a simplest case, most of the phones are having the features like sensors, sensors which collect your daily, location. If your location GPS is on, probably it collects your location map. Where are you going? What are you doing? Like everything is everything can be easily mapped with the camera feature, location feature. These are all sensors, right? Your fingerprint, your face recognition, camera for face recognition, for example. So, okay, maybe Bluetooth, or maybe your smartwatch is connected to your phone, and probably it is collecting all your health parameters. So several sensors are collecting lot of data, and through your mobile phone, probably it is stored on your phone, or probably through your mobile phone it is stored in the internet clouds, or whatever it is, right? So basically, it is first collecting into your phone, and that data is becoming if the system is weak, your phone is having weak operating systems, then there is every chance that the attackers can basically enter into your system and try to access this kind of important sensory information, or probably like as I told you, with images, videos, right, or anything as such. And probably your banking credentials, maybe your credit card information, your transaction details, your net banking details, right, and maybe SMSs, OTPs, right. Several things are things can be easily accessible through your what is called phone, right. And apart from all these things, probably your phone is also having easy access for the attackers to get into your contacts, your all other types of messages, right? And like SMSs or social media messages, whatnot. Like everything they can easily access. And in the worst case, if they are able to access the log files which collect the activity of your mobile phone, that is also sufficient enough to analyze and there are a lot of cryptanalysis techniques through which people can easily figure out what is happening on your phone, right? And mobile phones, unfortunately, in fact, it is easy to access, right? But in the context of attacks, it is unfortunate that like they are wireless based, and the wireless systems are much higher prone for attacks, and they lead to easy privacy breaches compared to the wired systems. So this is another reason why mobile phone based systems are really challenging, and they are actually meant for the attacks. Yeah, if you see the statistics, excuse me, if you see the statistics, in 2000, the very first ever mobile malware was detected even on the GSM devices, like the basic phones typically. Okay, and at the time there was bulk SMS attack was there. So there is some sort of denial of service kind of attack was created in 2000 period. And since then there are drastically increase in the number of attacks that are created on a phone. And if you see 2004, there was a first ever mobile malware on Symbian operating system, and it was spread basically through the Bluetooth and like at that time McAfee and F-Secure kind of different players were there. They actually became kind of consortium, and they tried to figure out the number of samples. Near about 400-500 samples were collected, samples of attacks, okay, malware were collected, and they tried to analyze and figure out the solutions to deal with such attacks. And later, in around 2009, there was a first ever mobile malware on iOS detected, and in 2010 there was first ever mobile malware on Android operating system also identified. And this was basically through media player. And later, around even the same was in the case of iOS operating systems. But the interesting part of Android operating systems is that uh, from 2010 to 2012, near about 2 years period, we have seen a big surge in the malware samples collected in in this case it was just 2 years, uh, only 400 samples they collected, but in 2 years there were almost 12,000 samples were collected. And you can notice that how the penetration of the attacks were there on the Android phones. And by 2002 to 12 to 2000, around 2000, I think 18, okay, it was almost in millions. the attack samples were detected were near about in millions, almost like 5 to 6 millions. So there is a big surge in Android-based attacks. So this itself shows that uh, how weak the Android operating system is. Anyhow, we will see this slide. So if you see this slide, you can notice that it is in millions and the number of malware samples, and every year it is growing in like almost like exponential. After 2016-17, there is slightly reduction in the uh, the number of samples increase. Otherwise, there is always the Android systems are so weak that there is always a possibility of attacks over these systems. Okay. Okay. So the next important question is why only Android? Why other operating systems are not having this problem? Okay. So motive is of course financial gain or identity theft, or these are the typical kind of attacks that we see in the case of uh, in general any mobile phones or any desktop based systems. But the attack sources are quite wide in the case of mobile phones, Android based mobile phones compared to other ones. So let us understand why it is like that. So if you see the first and most important uh, weakness is that Android phones are they allow the installation of your applications through Google Play Store. Okay, and the another important weakness of Android based systems is that uh, even they allow other than Google Play Store, any third party sources, they allow access to installation of any application from any source. You can get it from your email link, you can get it from websites, you can get it from your WhatsApp messages. Anywhere you get it, just you click on the link, you install the app, is possible in your uh, Android based systems. And this is not true in the case of other operating systems. They refrain installing any other applications if they are from the third party sources. So this is the fundamental weakness. And another important weakness of this Google Play Store is that they use a tool called Google Bouncer. So this Google Bouncer is just a emulator. Hope you know what is an emulator, right? So these emulators are having, they are not the real mobile phones, right? So whatever the new application you are submitting, let's say you are the designer, developer, you developed an application, and for the Android phones, and you requested Google Play Store to keep that particular application in its store. Okay. And anyone who is interested in that application can download and install onto your phone and use it. This is the routine procedure. So when you are submitting your application to Google Play Store, so what they do is they run this application first initially on the bouncer, the emulator, and if there is no malicious activity identified, then typically that application is treated to be a genuine application, and it is installed into your Google Play Store. But the emulators are having the biggest weakness is that they basically don't allow you to run the dynamic code. Dynamic code means, like, let me not mention much about it at this moment, but so suppose whenever you install an application, it appears to be genuine, but typically when it is going for the updates, then during the update time there is no possibility that these updates are always verified. For some applications it may be there, but for some applications they may evade, they may skip this possibility. Okay. So these emulated environments are not real time actually. They will not be able to detect the real time attacks. So that is a major weakness of these Android phones. So this majority of the applications, they appear to be genuine. Okay, I mean, off late, if they, I mean, if the Google found some application to be malicious, if some device already got infected, then they're removing it from the Google Play Store. But by the time the corresponding installation file is called as APK file, okay, and that APK file must already have been into the market from other third party sources, and like people can install the same application from different sources. Okay, so the point I'm trying to mention that there are other easy infection vectors through SMS, Bluetooth, internet downloads, and many other third party sources. People can easily uh, download the applications, and that applications need not be even at least Google bouncer is there to verify a particular application is genuine or not in the case of Google Play Store. But if you are downloading it directly from SMS, Bluetooth, or any other internet sources, then there is no scope that you actually verify a particular app is having infectious software or not. Okay, so that is the reason why the attack vectors or attack chances are very high in the case of Android phones. Okay, so there could be several, as I told you, update kind of attacks. There could be some download based attacks. Typically, we call it as drive-by downloads, right? There may be SMS, Bluetooth, kind of several sources are there. And another reason why Android is that uh, of the code is accessible, and attackers will go through that code, will try to understand the code, and they try to figure out what are the intrusion sources we have, what are the weakness, what is the weakness of that code, uh, through which particular weak point I can intrude into operating system, or I I can disable some of the features, I can uh, like you know uh, create some sort of attack into the system. So people can easily figure out the sources of weaknesses through which they can generate the attacks. So being the open sourceness of the operating system. So these are the primary reasons why Android operating system is really important. Okay. Yeah, otherwise, these points a couple of minutes back we have already discussed. Just to quickly to summarize, these are the typical malware threats we have. So basically, the fundamental goal was to leak the information like account details, contacts, call logs, or device related details, or create some financial loss, or create some financial threats. One sort of threat could be sending large number of SMSs using your phone, okay, to some other devices. Then that may be chargeable sometimes for you, right? And in the back end of your phone, background of your phone, probably the application may be making a lot of calls to other systems, or indirectly they are deleting the data of your system, right? So there is a possibility of economic loss, right? On other side, it may be having system damage, like for example, if your device is having some application running in the background continuously without your notice, and that may quickly drain out the battery, right? And disable some of the system functions, or change system configurations, many things they try to attack on your systems. And another last and final important reason why uh, malware attacks could be they generate the botnet activity, like they make your system to be an infected system, and they launch denial of service attacks from your device. So your device becomes one of the source of attacks on other devices, right? And otherwise, the click fraud or phishing, right? A kind of several types of attacks could be there. And other than this, there are many other types of threats are coming up these days. Typically, cyberbullying is also there these days. A lot of spams are created over phones, and social networking related attacks are also increasing. There are day by day attack sources are increasing, and that requires attention to deal with. Okay, so that then comes the important concern: how to deal with these kind of attacks. So basically, as I told you in the beginning, there are three different types of detection models proposed in the literature, basically called as static detection models, dynamic detection models, and hybrid detection models. And given different types of mobile applications, like for example, some of the applications may be malware in nature, some of them may be normal or genuine in nature or benign in nature. Okay, so you feed all these applications data set into your algorithm, and then that algorithm um, checks if a particular data set is having um, any weaknesses based on the model what you designed, and it tells you malicious or not. Okay, a particular application is malicious or not. Okay, so in this context, I must tell you that your Android operating system is having several internal features. One of the important feature is there is a file called manifest file, and using this manifest file, it stores several important features of your operating system. One of the key feature is the permission, and there are many other features such as intents and system calls and API calls, and many others are there. Okay, and one of the key feature is the permission. So you must be those who are using Android easily application. So first of all, what it asks is the permissions, like permission to use camera, permission to use your mic, permission to use your internet services, right? Like that. So there are around like 250 plus permissions, and some of them may be relevant to that particular application, and that particular application requests for these specific permissions from the user to whether allow these permissions for that application or not, or they are trying to the Android system is trying to seek your permission, whether, I mean, you trust this application or not, whether this application is safe or this application is safe or not. Okay, so this can be done through one of the feature called permission. Okay, and this is the fundamental weakness of Android system, because most of the users they give the permission to a particular application. They don't know whether a particular permission is relevant to that particular application or not. So most of the times, in fact all the times, what the users will do is, even including me probably, okay, what they do is whenever you are installing an application, you are doing that in certain hurry, and whenever it is asking for the permissions, you never even read what is the permission it is asking for, and just click okay, 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 then that application is installed. And this is one way the intruder enters into your system, and you are giving the permission to that intruder that you can use these particular features of your system. Okay, like use camera, use video, use audio, use gallery access to your videos, use internet services. So why all these are important? Because if you are giving, let's say, permission to use your gallery as well as to internet, then there is a possibility for the application to send all the images of your folder in the background to their the source, because it is also having internet permission, it is also having uh, uh, the access to the folders. So this is one important source from which the attackers may actually um, take the advantage, and with your permission they may create the attacks. Okay, so this is one way we can restrict the access to the attackers. Another way what they can do is they can actually use internet services. So all the network features, they may utilize the different attack sources. They may create the attacks through internet, and in soon we will see above 95% of the systems or the applications basically use network access, and this network access is actually another source of attacks, and that's where we have to figure out like what sort of attacks are created. So static detection algorithms focus on permissions based systems, or typically the manifest based systems, okay, where they see what are the specific permissions or intents or like a system calls. These are the static features of your uh, Android system, and using that we can also analyze, we can also figure out whether there is a possibility for uh, attacks. Okay, so in this direction we designed a model uh, around like with the name permission pairs or perm pairs, okay, which is based on graph based malware detection. Okay, and the second one is based on dynamic features. So dynamic in the sense like the network features are not static, like permissions, let us say, for a particular application once given are static, like fixed. They mostly change, don't change. But network features, they keep on changing, right? Uh, at this moment they may use some sort of network activity, and after some time the attackers may use different sort of attacks strategy. Okay, so dynamically the attack strategy changes over the internet, the how they behave, the network activity, sorry, how they behave in the network communication. Okay, maybe I'll give you a simplest example here to make it simple for you. So when typical the attacker's mindset is that they wanted to hide for longer times, and they appear only for shorter period of time, and in that shorter period of time they try to complete the attack. Okay, this is like typical attacker behavior. Okay, need not be always true. Okay, but this is a typical attack behavior of the attackers. Okay, the point is when we trace the network activity, if they are there in the network activity for the longer times, then there is high chance that you may easily catch them. So that's why what they do is they try to send smaller packets, and only for certain duration of time in a particular day, let's say couple of seconds, and disappear for the entire day, again they come again next day. So like that they keep on changing their behavior, and sometimes they are active only in the night times, not in the day times. So like that they try to dynamically change their behavior from time to time, and network features are one sort of source which you have to analyze and figure out how they are actually behaving. Okay. So in this direction, we proposed two different models. One model is based on ranking, and another model is based on clustering. And most importantly, some of the malwares basically use encrypted communications. So it is much challenging to detect such encrypted communications compared to uh, unencrypted or non-encrypted communications. Okay. And there is a possibility for combining both permissions and network traffic features together and create a detection model. And in this direction also, we proposed two different models. One is frequent patterns based, and another one is machine learning based models. So these are all different models we proposed in our from our laboratory, which uses different sort of data sets and design some algorithms around it. Okay, so let's quickly understand a couple of models around it. Okay, so here let me explain the first one. As I mentioned, every application requires permissions to access the Android resources, and whatever the application it is, whether it is malware application or whether it is benign application, both needs permissions, and only through permissions you can actually access the Android resources. Okay. So as I mentioned, there are large number of permissions, and selected permissions are given to an application, and using these permissions, the application tries to either creates the attack or probably may not create attack. If it is not creating attack, it is benign. If it is creating attack, it is a malware one. Okay, malicious one. Okay, simple. So this is a strategy. Now the question is here, we have to figure out whether a particular application is malware or benign based on we these features. What features? Features here, the permissions. What permissions a particular application is asking for. Okay. And if these permissions are contributing for any attacks. Simple. So there is a lot of research around this direction, and many of them use machine learning algorithms on permissions, and they try to categorize, clusterize, classify, like several techniques they use to figure out whether a particular Android malware system is uh, sorry, Android phone is having malware applications or malware behavior. Okay. But these algorithms are figured out to be complex in nature and in terms of time complexity, majorly. Okay. And another important reason is that these algorithms require many times the algorithm to be run on the servers. Okay. Okay. And to simplify the complexity of these algorithms, we thought of a different pattern here. Here, instead of considering all the permissions, we focused on only those permissions which make sense in the context, like figure out the patterns, the permission patterns, which combination of the permissions are actually leading to attacks. Not all the permissions may be contributing for the attacks all the times. So we need to figure out which are the specific patterns are actually leading to attacks. So for instance, there is option called read phone state, the permission called read phone state. Okay. This read phone state is almost like you are giving the permission to know the status. It's only the status, of course, but like it is something like your log, right? It provides network status, battery status, screen status, Bluetooth, all the sensors status, the camera, calling, whatnot. Like all the permissions, whatever are there, near about, as I told you, 250 around. Okay, all the permissions status it provides. What I mean, everything about the permissions, right? And this information is attached with internet permission, then there is every possibility that that application may send to their bot master, the attacker, okay, who wants to know your phone status. So this phone status details can be sent to the bot master, the external world outside, through the internet. So these two permissions are enough to basically send your internal details to external world. So you have to be cautious while, that's why you have to be cautious while giving the permissions, whether that application really needs this permission or not. Okay. And uh, in this work, we are trying to figure out which specific, combinations of features or the permissions are actually leading to the attacks. Okay. So when we started this work around like 2012, 13, uh, 14, 15. So at that time, none of the works were having the idea around this, and nobody proposed any idea around this. So we took this as a initial idea, and we proposed this research. And in this one, the goal was how effectively use permission patterns so that they help in detecting the Android malware. Okay. And in our contribution, we designed a model called PermPair, and you can refer to this research paper, which is in IEEE Transactions on Information Forensics and Security. And you can find wonderful, it's almost like 30, 40 pages, 30, 32 pages paper it is, and you can find every minute detail how we designed this algorithm, how we developed the algorithm, everything is there, how we analyze the algorithm, right? Everything is there. And in this one, instead of using the routine machine learning models, we adapted the graph representations so that we link those permissions into the graph. We add those permissions into the graph and construct different types of graphs like malware graph and benign graph. And in the malware graph, there are different types of datasets we have taken, and for each dataset, we have constructed different graphs, and all these graphs together, this benign graph, we try to give the credit scores, and based on the scores, we try to analyze how what specific patterns of these uh, like in the malware samples, what specific patterns are contributing, so give some ranking of all these patterns. At the same time, in the benign apps, what specific patterns are actually contributing for internet access or whatever it is, like. So in this direction, rank all the uh, permissions, and based on those permissions importance and how they are contributing into these graphs, we designed an algorithm to help in detecting the malware impact. Okay. So this is one of the wonderful paper. I strongly recommend to everyone to go through this paper and understand how the attacks are actually constructed in the detection is actually detection models are constructed basically using these permission pair solutions. Yeah, another important direction around this is the dynamic detection. And as I mentioned, the dynamic detection is all about network features. So typically some malware samples, as I already mentioned earlier, they behave as benign applications while they are coming into Google Play Store. Okay, and when they are installed onto your phone, even if your phone is having some antivirus software, then they try to uh, appear like the benign applications, right? But of late, when there is a need for updates, then at that time they start that means permissions wise, when you install the application, you give the permissions, and permissions wise they appear to be good. Okay, so your static algorithm gives this particular application as benign application, genuine application. Okay, but this is not a genuine application. This is actually a malicious application. It generates the attacks during its update time. Whenever there are updates required, so in the name of updates, they actually start downloading the malicious samples, malicious code into your phone, and they actually attack on your systems. Okay, so at this time we have to understand, during the network activity, when they are downloading the content, are there any possibilities of malicious activities by the specific application? Okay, so for that, this is what we call it as dynamic feature. Okay, so network traffic features are basically the dynamic features, okay, which we use to create the detection model. Okay, so network traffic feature, so in the slide itself, you can read now, typically they are extensively used in desktop based detection systems, and they are not actually used for Android malware detection models. When we started this research at that time, okay, and many of the works, even if they have used it, their focus was feature selection and what are the specific sources that are actually, specific features that are acting like sources for the attacks. Okay. So our goal of this research, because again here, no one focused on finding out what are the specific distinguishing features that that contribute to the attacks. And in this direction, no one was working at that time. So we are the first people, maybe from India, to start this research. And it was around 12-13. Okay. And we designed a wonderful model around this. And that was very much appreciated in the conference. So in this case, the problem statement is how to detect Android malware based on network traffic features and figure out which specific features that help in distinguishing these normal applications and malicious applications. And for this purpose, we developed a model to prioritize the network traffic features, categorize or classify whether the specific feature, network traffic feature, is contributing for malware or benign purposes. Okay, so give some ranking for them, how impactful they are. Yeah, so why to use network traffic as detection feature for Android? So as I told you, most of the Android phones, Android malwares use network activity. It's more than 93%, and uh, the algorithms which proposed earlier were not having good accuracy, and there is always a need for improving the accuracy of detection. Okay, and there were very few works proposed in the literature at that time and analyze the network traffic features. And fortunately, as I told you, there are only two works, and one of the work is from our team. And that work, the previous work, this one, like the 11th work in this paper, we initialized this research again, like with an emulator from our laboratory. We captured the network traffic features from the emulator, and we noticed that out of 16 traffic features, we found 7 are distinguishing traffic features. That means using these 7, I can say that this particular this particular application is malicious and this particular application is benign. Okay. And there were some malware like Anserver bot or base breach, these kind of uh, applications, malicious applications, in fact, they are waiting for certain system related events that are not actually possible from emulator. Like, for example, one typical feature is calling, for example, or SMS messaging. Okay, these kind of features typically are not possible on the emulator because emulator is not having any SIM card. Okay, so it's not possible to make a call. It's not possible to send an SMS or something like that. But you can, of course, internally verify the behavior of the application. Okay, so in this work, this is the first work we started, and that is published in this conference. And you can go through this paper for basic idea how we did it and how you can start. Doing these kind of works on the emulator itself. Okay, and after this, we actually, since we got very good appreciation on this work in the conference, so then we got motivated and we actually bought the actual like smartphones. We purchased some of the smartphones, and we started capturing the malware traffic on these smartphones. And the weak part of these smartphones is that, like, once your like phone is attacked with the malware sample, even if you format, sometimes it may not leave the device. So we have to waste that phone, and we have to buy a new phone and again do it. So it's really a costlier effect, but still we took it as a challenge, and we experimented on the real phones. Okay, and we repeated the same experiments what we have done here on the actual phones, and we slightly instead of 16, we slightly increased the number of traffic features. We gone up to 22 now this time, and surprisingly, on the emulator we found 7 distinguishing features that classify whether malicious or not. Okay, but surprisingly, there are no distinguishing traffic features identified um, in this case. And this is the starting point of our research, because this is really challenging. On the real phones, they are evading the attacks. So then our idea of figuring out whether it is malicious or not changed. Then we focused on figuring out what are the basic set of features actually, or you can rank these features in such a way that they tell us whether a specific application is actually contributing for the attacks or not. Okay, so in the process, we took several data sets. In the beginning, we started with like 2 sets of data sets. We classified them into known and unknown samples, and some of these data sets in the beginning were from genome data set, and the size of those data sets are pretty smaller, near about 200 samples. And out of 200 malware samples, we used, I think, near about 150 for testing. And there are near about 100 normal samples, and we used around 80 for testing. And we classified them into like uh, known and unknown samples. So training set, testing set, known samples, unknown samples. So we classified them, and malware and benign. So all these combinations of samples we have taken, and we uh, started analyzing those traffic features. And after that, we have used several other like data sets apart from genome data sets, like CUDAS or Trabin or something like that. There are many other sources are there. Okay. Then we started analyzing the traffic features, and we noticed that, and in fact, we tried to rank them, uh, rank those traffic features. So first, let me list what are those traffic features we considered, and what is the range of those traffic features, the values that are contributing. Okay. So, for example, you take average packet size. As I told you, attackers most of the times try to be smaller durations of the times over the network activity, and their packet sizes would typically be smaller in size, so that they skip the detection possibilities. And most of the times they try to, like, many times they try to see whether a particular device is in sleeping mode or active mode. So for that, it doesn't require, like, sending of the data, receiving of the data during that time. So they frequently poke the phone and figure out what the phone activity is. That requires very small size of packets. Okay. So that is the reason why we considered one feature average packet size, and see uh, how each, like, uh, packet, whatever it is going through the network activity from each and every application, we try to analyze what is the range of packet sizes we are having. And since we are already having the malicious data sets, and from all the malicious data sets, we noticed that the average packet sizes were between like 72 to 388 in size. And when it comes to normal traffic, it ranges between 162 to 2300 plus. Okay. But the sad part is that, so from 160, sorry, so from 162 to 388, in this range, there is a commonness. That means malware samples are also falling, normal samples are also falling here in this range. So how to figure out whether it is malicious or normal? It's not possible to figure out, because it may be a normal one also. And if you notice this, like for every other feature we considered, as I told you, there were 22 features. If you notice, there is always, in every application or every feature, there is an overlapping of the values, and this is a weak part. So I cannot confidently say that whether it is malicious or not. Suppose if it is between 72 to 168, probably I may say that this is clearly malicious. Or probably from 388 to 2300 plus, I can say probably this is clearly the benign or normal application. But in this range, I will not be able to say whether it is malicious or benign. Okay. So like that, we try to analyze for every other feature. So there are almost like 22 features we considered, and we given a notation like F1, F2, and so on up to F22. And on these features, we noticed that, like, after the analysis, there is no distinguishing feature that helps us clearly to say that this is malicious range and this is normal range. All are having overlapping ranges for the normal as well as malicious uh, ones. Okay. So here where our focus came into the picture, and we excuse thought in a different fashion. And here we wanted to first analyze which features are actually contributing for the attacks. So we started thinking towards prioritizing the features. So for that, we used two important techniques: information gain and chi-square test. And it is IG is more towards reduction of entropy, and chi-square test is more towards how categorize the data, compared to expected and or theoretical to the collected data and so on, right? So based on these two important models, we started working to rank them. So as I told you, the purpose of feature ranking is multifold. It improves the detection accuracy, and other side, the most important point is it reduces the feature dimensionality. So rest is simple. We started adding one feature after the other to the list, to both chi-square test results as well as information gain results, and we started finding out true positive rates, false positive rates, as well as F score. And you know that like F score is something like balance between the precision and recall. Okay, so the this will tell us how they are actually contributing, right? So we slowly adding one feature after the other, and when it got this feature set, like F2, F19, F21, F1, F5, F16, F4, F10, and F9. So these are the features which are contributing to 96.36% of F score. Okay, and we further kept on adding more number of features, and you notice that there is no change in the accuracy. And you can also notice that at some point of time, adding more features is not actually helping, rather it is deteriorating. You can see this result. The accuracy of this up to 21 features was 96.36, whereas this is 96.07, less than the previous ones. So adding more features is not sometimes a good idea also. Okay, it may reduce your accuracy. So choosing the right features at the right time is also very important consideration that we have understood from this analysis. Excuse me. So then we try to take several combinations in this research, and we try to figure out whether these 9 features, whatever we have identified through this analysis, are the only way or there are any other possibilities. So we took only IG, only chi-square test, only on malware, only on normal samples, right? So we tried to take different combinations of possibilities. I listed actually only 4 here, but then we tried many. In fact, we tried different combinations, and from all these experiments, we noticed that this only top 9 features from both the algorithms combinations are actually giving the better detection accuracies. Okay. So the conclusion of that particular research is that, so out of 146 malware samples, out of 150 malware samples, 146 are identified as malware, and there are some false negatives from certain apps like Droid Kung Fu or Jobs or Genome. So there are a couple of applications which evaded this network activity detection just because they are using encryption techniques while communicating. This is really surprised us because uh, attackers are also using different types of encryption techniques to hide themselves. Okay, and when we analyze these applications, we noticed that some of them are using DS algorithms, some of them are using much complex AS algorithms, and interestingly, some of them are using their own encryption techniques which are not available as a standard in the market. See how people are trying to create the applications and how they are hiding themselves. Okay, and then this has become next big challenge for us, like how to deal with these kind of encrypted malware samples, right? So then we also try to analyze on benign applications, and 73 out of 80 were detected correctly. But again, there are some false positives here, like some of the online games and online news applications, or some mobile web browsing kind of applications. Uh, they appear to be malware, but actually they are not malware, they are normal samples. And those who are interested to learn about this work in more details and want to continue their research, they can read this paper. This is having wonderful presentation, how this particular work is actually being presented. Okay, and we have also tried to do a lot of research to figure out how encrypted malware samples are also detected. And this paper is not yet published, so I'm not discussing the concept at this moment of time, how we did it. Yeah, next important approach is hybrid detection models. And in this case, as I told you, it is a combination of both network traffic features as well as permissions together. So in the interest of time, I'll slightly speed up the presentation and I'll try to conclude in 5 minutes. Okay, so the problem statement is how to combine the permissions and the traffic features to develop a hybrid model. Okay, so here the contribution is we proposed two hybrid models, as I told you, combining permissions and traffic features, and uh, figured out two different models named as, so one of them is NTP Droid, and another one is a combination of both supervised and unsupervised learning techniques, machine learning techniques. And the first one, NTP Droid, you can find it here. Please refer to this paper. This is published in TrustCom, one of the top-rated conference. And I'll explain the second one now, very quickly. So we used both, as I told you, supervised and unsupervised approaches, and we used supervised KNN and unsupervised K-means variation, K-means algorithm. Okay, and since the malware sample space is bigger one, so we wanted to bring out this large such space to smaller ones by creating smaller like K-means algorithm, which clusters the large space into smaller ones. And on each small cluster, we apply KNN to figure out or to classify whether a particular sample is malware or normal, or particular cluster is malware or not. So this is very simplest way we can explain what it is, right? Okay. So we fed the applications, the data sets, okay, which are training applications, and from that we extracted the permissions, we extracted the network traffic features, and produced a combined feature set. Okay, and on this feature set we applied k-means to cluster several the large space of this data sets into smaller ones. Okay, and on that each cluster we applied KNN algorithm, and that produces the detection result. And same thing we repeated for testing applications also. So this is a fundamental structure. So just it is explained slightly in detailed manner how we did it. So take all the applications and extract all the traffic features. Okay, and instead of taking all the traffic features, we have taken only those 9 traffic features we proved that are actually contributing for the attacks. Those we ranked them in our previous research. So we consider only those 9 traffic features. This list is given here. Okay. And we also extracted the permissions from the manifest file using tools, different tools like APK tool, for example, right? And both of them are combined to construct a combined feature. All the network traffic features and all the permissions combinations. So you get a bigger, set of features from all the different types of applications with combination of permissions and network traffic features. Okay. Then the rest is very simple. You just cluster them, right? Like this. Okay. And once you cluster them, then we can actually apply KNN to classify them. What is whether a particular cluster is having malicious behavior or not. Okay. Often a question is asked like, why not K means, why only K-medides? So typically, our feature set is having a combination of numericals as well as strings. So K-medides basically more applicable for what is called string-based datasets. So that's why we considered it. Okay, and for permissions we used Levenstein, and numerical values we used or network traffic features we used Manhattan distance models. Okay, and same thing we applied on testing models, then applied the KNN to figure out whether a particular like sample is having malicious behavior or not. Okay, then we kept on analyzing on different data sets. We took normal samples, malware samples, and we tried to took different values of K for K-medides as well as KNN. Okay, and we tried to analyze this data. This is the most important part of it. And we try to analyze the data by considering different combinations of analysis. So again, we try to do it with only supervised approach and only combination of supervised and unsupervised approach, right? And notice that again we tried static, dynamic, and hybrid, all the 3 independent models. Again, static, dynamic, hybrid, independent models, and we tried to analyze the results. And you notice that the best result was like 89.62 detection accuracy at k equals to 9, right? And in this case, the accuracy is 93.77. So you notice that the accuracies are relatively much better in the combination case compared to the independent cases. So the observations are static gives least accuracy and hybrid gives highest accuracy. That's what we notice. And yeah, there is some ambiguity with the Levenstein distance metric, due to which there are the detection accuracies are actually low for it. And same is the case in the dynamic detection and hybrid cases due to Manhattan detection. There is this is the reason why there is some detection anomalies. But this slide actually helps you understand basically how we try to figure out the best accuracies. So see here, so this is a static detection, accuracies are pretty low, below 70s, and this is a dynamic detection, accuracies are near about 80s. Okay, and when you take dynamic detection, accuracies are near about 92, 93 percentages. Okay, much better than all these other ones. And we also noticed that after k equals to 5 in KNN, right, there is no big difference in the detection accuracies identified in this particular data set. These are the important conclusions we have made from this research. Okay. and there were no there are no big number of papers published at that time. Only 2 or 3 papers published in this direction, and among them they were using large number of features compared to our algorithm, and our feature set is much smaller compared to their feature sets. And some of them are not using detection algorithms, only they're using analysis purposes compared to our model, which is focused on detection, in fact. So the conclusion of that research is that hybrid detection gives better accuracy than static or dynamic, and the combination of unsupervised k-mediates and supervised KNN gives better detection rather than using the KNN alone, and accuracies are near about on an average 92%. And this is the paper which actually this research is actually published in Mobicom conference, which is another top rated conference in the conferences list in this direction. Yeah, there are many other possibilities to tackle with in this direction, and I recommend you to go through all these possibilities. And one of the biggest challenges dealing with encrypted traffic and dealing with zero-day attacks, right? And of course, improving the accuracy itself is another big challenge. And as I told you, some of these researchers, they use the servers for data analysis, finding the detection, and they send, like, from the phone you send the data to server runs the algorithm, gives the reply back to the phone. But this creates some delay, and it may not be real time always. So we wanted to design the algorithms which are runtime in runtime or real time in nature. So we also need to think about designing the algorithms which are of that nature. Okay. And apart from that, there are many other ways, like, for example, permissions are not the only category in the static case, right? There are many other ways we can actually deal with the attacks. So that's all from my end. Thank you so much for patient listening to my session, and I'm open for the questions now.
Excuse me, sir.
Yeah.
Am I audible?
Yes, you are audible.
Sir, okay. So how many centroids have taken 4K? See, there are how many clusters that you have formed, sir? Actually, here you have used k-means and also KNN, right?
Okay.
Okay. So how many clusters that you have formed?
See, as I told you, it depends on the K what we have taken, and we. Hello.
Sir.
Am I audible to you?
Yeah, sir. Audible, sir.
Right. So here is having only 2, because whether it is particular, like, malicious or not behavior. Okay.
Okay, sir. Sir, next after this k-means you have applied KNN, sir. So what should be the optimal value?
K is set to 2 to figure out whether normal or not. Yeah, please go ahead.
Okay.
You are asking something.
Yeah, sir. Optimal value for KNN, sir.
It's 3 in our
Optimal.
in our data set. It is 3. Okay.
Sir, in a dynamic model, so is there any kind of weighing mechanism adapted for the features, or even in case of considering the priority?
In dynamic
Dynamic model. when it comes to the features, adding the features.
Your voice is not clear.
Hello. Yeah, is it clear now? Is it audible now?
I'm slowly able to follow.
Okay, fine. So in the dynamic model, while the features being added, is there any kind of weighing mechanism taken into account, or all the features are being taken of the same weightage?
No, I already show you the slide. We kept on adding one after the other on this. Like, we took like feature one, then feature two, feature three. Just kept on adding all the features, and from that we figured out the optimal one.
Okay, it means that there is no weightage being associated with any of the features. All of are of equal.
No, there is
I-
maybe my voice is. So give me a minute. Yeah, here is. So here we figured out that these 9 features are contributing. Okay. And we then ranked them. Right? And after ranking them, these are the 9 features contributing. And in what order they are contributing? So this is the order: F2, F19, F21, F1, F5, F16, F4, F10, and F9. This is the order. Make sense?
Yeah, fine, sir. Thank you, sir.
ಓಕೆ ಇನ್ಯಾರ್ದು ಇಲ್ಲ.
Okay. Any other questions? Fine. Thank you so much. If there are no questions, thanks for your patient listening and nice questions. Yeah, we'll meet in some other occasion.
Thank you, sir. It's my pleasure to thank Dr. Satish Kumar Pedoju for providing wonderful information on what is Android, why Android, what are the different modules that are used to detect Android malware detection. Thank you very much, sir.
It's my pleasure. So shall I leave the meeting?
Yeah, sure.
Thank you, sir.
Okay, so we have one more session in the queue. From Emmanuel is Iran. I would request Iran to give a welcome.
Good morning all. I'm Sindhu, Assistant Professor in Computer Science Department, Pesce Mandya. Today in online we have with us Dr. Emmanuel S. Grant, Associate Professor and Associate Director at School of Electrical Engineering and Computer Science Engineering, University of North Dakota, USA, to deliver the keynote address on towards defining guidelines and ethical consideration for safety critical software system development. So I welcome you, sir, on behalf of Conference Committee, Icerect 2022, and call upon Shashank to read about the short biography of the Dr. Emmanuel.
So thank you. So it's my privilege to read a short biography on Dr. Emmanuel S. Grant. So he received from University of West Texas, MCS from Florida Atlantic University, and a PhD from Colorado State University, all in computer science. Since 2008, he is an associate professor in the Department of Computer Science and the School of Electrical Engineering and Computer Science at the University of North Dakota, USA. When he started as an associate professor in 2002, he currently serves as an associate director of the School of Electrical Engineering and Computer Science and ESEEC's graduate program director. His research interests are in software development methodologies, formal specification techniques, domain-specific modeling languages, model-driven software development, software engineering education, and ethics for software engineering. Emmanuel Grant has conducted research in software engineering teaching with collaborators from Holy Angel University, Philippines, Health University College, Malaysia, Tripillari, Hyderabad, India, Singapore Management University, Singapore, Mount Clair State University and University of North Carolina, Wilmington of USA, and the University of Technology, Jamaica. He is affiliated with the CMAC Software Engineering Method and Theory Organization as a member of Essence, Kernel and Language for Software Engineering Methods Group. Emmanuel is a member of Association for Computing Machinery, Upsil P. Ellison, UPE, and Institute of Electrical and Electronics Engineers, IEEE. So it's an honor and privilege to hear a talk from him. We have a recorded session since he's from US, so we'll get it played here. Kindly all enjoy.
Good day and welcome to my presentation on software engineering formal specification methodology in safety critical system development. My name is Emmanuel Grant and I'm a professor, associate professor at the University of North Dakota in the United States. Now, safety critical systems are systems that are characterized by their failure resulting in possible harm to persons who are using the system or to others in the environment in which the system is being operated. There's another aspect to these type of systems, those that may cause damage to a reputation or viability of a company, wherein if they fail, the company may incur such financial property loss or reputational loss that could be harmful. And those we call mission critical, and we see them in two different areas. But the safety critical ones are the ones that impact life. Software engineering is that full encompassing of software development that we are more familiar with the use of the implementation, coding, and testing of systems. But software engineering covers other broader aspect where we have processes and techniques for capturing the requirements, designing the system, implementing it as well, that is a code development, testing and evolving the system over time. And so we focus on that full gamut of tasks and processes that are necessary to produce system. So some of the examples of what we deem to be safety critical systems are those such as in avionics systems. These are systems that are used both on board aircraft and on ground in order to maintain communication and control over aircraft. UAS systems are one of the growing areas in avionics, and this is where the safety criticalness comes into play at an even higher, just as higher level as when we think of commercial aircraft. Patient health monitoring systems, another area of safety critical operation, power plant control systems, and these systems have been in the news quite a bit because of the security issues surrounding them, wherein there have been a number of attacks, hacks into power plant systems in the US and in other nations. We have heard about this happening in the ongoing war with Ukraine right now, where there have been attacks on their power plant system. And of course, there's the area of motor vehicle operation, where we're looking at these self-driving motor vehicles. And this is another area where the critical operation is of high importance. Now, when we talk about software engineering methodologies now, there are a number of different approaches that are in use there. We have what we know that traditionally the development methodology used has been the waterfall, and it's argued that all other methodologies have sort of evolved from this waterfall model. But today we have new different approaches that are applied in different domains. For instance, we have what is currently one of the more popular ones, the model-driven approach, which is used in conjunction in developing safety critical systems, and it's an area where I've been focusing a lot of my work. There's also the area of domain specific, what I refer to as product line, where you look at developing systems for a class of problems and not just a single problem type development. And of course, the agile model, which has exploded in the business world. And so these are just a few of the methodologies, software engineering methodologies that are in play. Now, why is this really a big deal today? The idea of developing system, particularly safety critical system. We look back over time and we have seen that there have been a number of failures that have catastrophic failures that have cost lives. One of the most famous ones, or infamous ones, that have been researched and written about extensively over decades now, is that of the Icerect 25. Icerect 25 was a radiation X-ray machine, and it failed a number of times, resulting in the death of, I think, either 4 or 6 patients, injury to a larger number of patients, before it was recognized that there was a problem. And so what they've learned, because of these failures, we have learned quite a lot. And one of the key things that came out of the Icerect 25 was this idea that software specification and documentation should not be an afterthought. And again, this is the idea that we have to apply very rigorous development methodology in building systems of this nature. So this is an image of what the Icerect 25 looked like. How it operated, so it operated in 2 modes. In one mode, it provides radiation treatment, cancer treatment for patients, and so it has a targeted, low energy radiation beam that is projected onto the patient's body, targeting the particular area of treatment, internal or external. And this, because it's low energy, the treatment would last for extended periods, might be a few seconds or even probably as much as a minute of radiation, low energy on the patient's body. That's in one mode. It can then also be converted to work as an X-ray machine. In this case, it produces a wider spread beam, high intensity, high energy, for a very short period. It's taking a photograph. And so it's a burst of high energy that is intended to penetrate the body, striking the plate here and creating an image on the plate under the patient. But it's just as how we take our pictures today. We click that shutter button and it snaps it in fractions of a second. That's how the machine operates. But the software was changed. It used to be a manually operated machine where an operator had to change a handle in order to get the operation to switch from one mode to the next. But in this case, they decided that they would convert it into a software machine, and so the software controlled everything. That physical switching was no longer done by the machine. Result is that the software failed, and it produced high energy X-ray beam at times when it should have been producing radiation beam, and resulting in the death of persons. Another major failure that occurred was the Ariane 5. French-operated rocket system. They had been operating what was known as Ariane 4, and was very successful with taking payload up into space, putting it in orbit, taking supply up to the International Space Station. But then because of the high demand for that service, the French aerospace industry decided to build a larger, more powerful rocket, the Ariane 5, which would take up larger payload on each lift. One of the things they did was simply copied over part of the navigation system from Ariane 4 onto 5. That software system was not tested for 5, and consequently what happened is that it failed because of the idea that it worked on 4, so they assumed it would work on 5. But 5 was a different operational environment, and they failed to recognize that. And this is one of the things, again, where we need to have a different approach to how we build these type of software systems. Here's just a graphic of the rocket as it was designed. So at first launch, it had to be destroyed in flight because of the failure. Another major failure with aviation, although this was a lot of pilot error involved here in this Air France 447 in 2009. One of the newest Airbus aircraft, the A350, literally fell out of the sky. And part of it was, as identified here, there's a lack of a clear display in the cockpit of the airspeed. Inconsistencies identified the computers. So the software system recognized that there was an airspeed anomaly, and that it was getting bad reading for the airspeed indicator from an external sensor. And that critical piece of data was used to control a number of automated operated software system on the aircraft. Once the software recognized that the value it was getting from the sensor was invalid, what it simply did was turn off these automated system. It turned off the autopilot, it turned off the thrust control. But it didn't notify the pilot as to why these systems were being shut down. And so the pilots reacted in a whirl of uncertainty as to why this happened. They responded in the incorrect way. And again, from the report on this investigation about the Air France failure, it was determined that in-service feedback is an essential prerequisite in the process of improving flight safety. And so again, it is these safety critical systems have to be developed in ways that go beyond just what we do for systems, in which if it fails, we can just simply do our Control Alt Delete and restart. These systems cannot be operated in that way. Now, this is just an animation of that Air France crash and how it occurred. This is an animated image. Let's see if it will work here. No, it doesn't. But what this depicts is that it depicted how the system would have operated while the pilots were in control of it, things that went wrong, and the reason why these things went wrong. It's hyperlinked. It should have been hyperlinked, but I failed to have it done so in this presentation. I apologize. So one of the things that I've done in my research is look at this use of what we call domain-specific modeling language development environment. And here it's a model-driven environment. So a number of these development methodologies that we talk about can be overlaid with each other to create development methodology specific for certain domains. For instance, you could be working in the avionics domain, which is where I've done some research here, and I'll address that in this presentation. It also may be applicable in things like in the medical field. If you're developing medical devices, that is a very specific domain, and you would work towards capturing certain knowledge about this environment and codifying it in some ways that developers can use the knowledge of experts while data developers themselves are not at that expert level. And so this schematic here represents an attempt at doing something like this. So within this, I'll call it yellow boundary, this isn't the area of activities that results in the creation of a modeling language that is specific for a particular domain. So I'm going to talk about avionics quite a bit here. So let's say you're developing a system for onboard aircraft software system, avionics system, and this is a highly critical area. So we will go about capturing requirements. So what happens in this first activity here is that from all the stakeholders involved, we try to capture all the known requirements that is needed in this environment. And this domain requirements engineering effort is a massive one. It's the front end of everything. And so the idea is that you want to capture all the necessary, all the known, and strangely enough, people will say all the unknowns as well. Information about what happens in that environment. Once you have that, then you will carry out a series of activities, engineering activities on this data in order to identify what is relevant, what is required, what is optional in any application that is being developed. And so you're looking at trying to understand all possible development that can take place in this domain and not just with respect to one application. And so as input to this activity, you will have information from the stakeholders. And stakeholders include almost all the players that could be involved there. The engineers, the pilots, the managers, the owners of businesses. So you get information from all of them. Engine manufacturers, all of these people would have information that is pertinent to this, and so you get it from them. Coming out of that is a set of precise domain requirement specification. So this specification now identifies the functionalities or services that are desired in this domain. And again, keep in mind that this is not just about one application, but you're trying to capture and codify information about all possible applications that could be developed in this area. We will, as input to the requirements, we will have formal and informal notations, and we're going to see some of that later on. And so once you have completed the domain requirements, then you can transition over now to the analysis and design. So this is where you start looking at here in the domain requirements, we seek to identify the problems, the issues, and over here now we start looking at solutions for those problems, those services that are required. How do we go about providing these functionalities? And this is where that work commences in the domain analysis and design. When we're here, we may find that there are some requirements that are incomplete. And so we would have feedback into the domain requirements engineering activity, which may then result in feedback loop. So we can either refine a requirement, elaborate it, or capture more. Right? And again, we use formal notation and informal notations in this area. Once that is complete, we will produce a set of models at varying levels of granularity. High-level design, low-level detail design, and these will pass over into what is known as the domain language engineering area. And so what we do here now is develop, just as how we have a written language where we have letters of the alphabet which you put together to form words, and we put words together to form phrases, and we put phrases together to form sentences, and sentences together to form a paragraph. Paragraphs come together to tell a story. And it's the same kind of a paradigm that we look at here, because this language here has a set of modeling concepts. And just as always with written language, we have rules as to how we can put the letters together. We have rules how we can put the words together. And we have rules how we put the phrases together. And this is what we refer to as the grammar of the language. Similarly, with our work here, we have these modeling concepts that are graphical. They are not textual, as with our language, with our written language. They're textual, and then we simply come up with a set of rules, domain-specific development rules, and this forms a grammar, so it tells you what components can be linked together, and if you're linking these components, what are the things that can be changed, and what are the things that are not to be changed, that kind of way. And out of that now, we have this modeling language, and this modeling language now is the language that we use at the application phase, which is in this purple area. So now I have a language that defines all the possible components in my application domain and a set of rules that tell me how these components can be put together. I have that language, so it's the syntax and the grammar I have now. And when I go to do development now, and by the way, the work in this yellow framework here is done by experts. These are people who are very skilled at doing requirements engineering, using formal and informal notation, doing domain analysis and language design. But the language they produce now is input to the application engineer. And this can be a junior, some of you just graduated out of college, you might find yourself where you're required to work on a project and develop some component of it. And so if you're using this language for that particular development environment, it will have a set of rules that say, what are the requirements that you wish to instantiate in this application you're building? And you specify to this that the languages, that the functionalities are of this kind, and then it will identify the components that are appropriate for satisfying for implementing those functionality, and there's always a tool support environment for it that is done in, and then you could plug and play these components. It will tell you what you can change, what you can specialize for this particular application, and that is the essence of it. So what you have here is codification of expert knowledge that can then be used by the average developer in producing safety critical system. Now in avionics, there is a requirement for system to be developed along a certain guideline, specification. And that specification in the US is known as the DO-178C. And it has a set of, so this is the main document, the DO-178C, and it has a number of associated documents. So this sets out the specification for airborne system and equipment certification. And supplementing that is a document tells you what sort of software tools you can use and how you must use them, what sort of model-based development and verifications you must do in developing these systems. There's another document that talks about object-oriented development as it applies to this environment in which you're working. And then there is a document on the formal specification, formal methods that can be applied in software development. And so how this document is applied is that any person developing avionics system, before it can be put on an aircraft, it has to be certified by a set of engineers who are independent of the developing organization. And they go by this specification, so they will come in after you say you have developed your software. They will come in and they will go through this, looking at your system, go through the specification and see if you have abided by what the specification requires. One of the first things the specification does is it asks you to establish what level of criticality your software system is at. And so they start off at the bottom here at a level E, and it goes upward to the most critical, which is a level A. And here are some example description of what these levels are. So at the very bottom, you have a software system that operates the onboard entertainment system. And so the idea behind this is that if the entertainment system fails, the aircraft still operates. I mean, passengers may be disgruntled if they can't watch their movies or play their game or listen to the particular music they want to listen to through the system, but it doesn't impact the operation of the aircraft. At the very top now, we have the primary flight display. So this is the flight control system, wherein if they fail, the craft could become inoperable, resulting in death. And particularly almost every aircraft that is being manufactured today is manufactured by what we call a fly-by-wire. It's all automated, software controls everything today. The communication, the flight control, the entertainment system, it's all software managed. So we use, in software development, we use this modeling notation known as the unified modeling language. And these are just some of the examples of the models developed and used in that domain. And so these are the graphical models that are built by software developers now doing model-driven development in safety critical system world. Now, my research looked at this DO-178C document, and what I do with that is a very textual document. It's all written stuff. There's just a bunch of tables at the end, textual tables. And so it's very hard to use because the document is very interrelated. So almost every section reference another section somewhere. And sometimes one section will reference multiple sections. So one of the efforts I've made in my research is to take that document and to transform it into UML models. And so this is an example of one of the, this model is known as a use case diagram. And what this model does is just capture the high-level services that a system would provide to a user. You can almost, although I say this guardedly, you can almost think of these things here. They are services provided by the system that is being developed. And you can think of them as being almost like the tabs on your interface screen once you start an application. So what I've done is taken this model and use it to represent some of the main functionalities that have to be carried out based on the DO178 specification. And so we have a stick man out here which is referred to a user. So this person, this entity here, will be using these services of the system. But I'm using this model not to model a software system, but to model a process for software system development as specified by the DO178C. So one of the things that the DO178C requires you to do is to develop a software plan, develop your software standard, select your software method, select your software tool, and then once you have done all the selection, you then have to go to what is known as you validate it, and you may have to revise this entire plan that you started out with. And then you also have to plan for additional consideration. So those are the what if situation. What if I don't have a development tool to carry out this particular activity? What is there to be considered? So I'm using the UML, which is designed for software development, to model a software development process. So it's an abstract in a way from the system to the process that develops the system. And so one of the things we talk about one of the things we do in simple rigor system development is that we talk about use of rigor. Rigor is doing things in a scientific manner, a systematic way. And at the extreme end, when rigor is taken to its most extreme point, we have what is known as formalism. So we're using formal notation, formal ways of doing that. And formal in that sense being mathematical. So for instance, one of the rigorous ways in which we develop software today is that let's say you have a function in your code that hooks a flight. So there's a function that does a flight hooking. And so a rigorous way of ensuring that this function will work properly is to establish preconditions for that function to execute. So there are certain things that the system must be in a certain state in order for this function to execute successfully. And we specify those as preconditions. And then once the function has executed, it may or may not change the state of the system, but we have to recognize what will be the state of the system at the end of the execution. And these are known as post-conditions. And so when we do rigorous analysis now, what happens is that we establish these preconditions, we then look at how the function executes, and then we look at, so if these preconditions are met, then the function can execute. If these preconditions are not met, then that function should not execute. And so if the function then executes, assuming the preconditions have been met, then we examine the post-condition state of the system after the execution and try to ensure that if the post-condition is not met, then we know that something went wrong in the function and therefore the function did not execute correctly. And so, so this is the abstract view, and then you could look at a while loop in your program. And so in order for this while loop to execute, there are certain conditions that must be met. In order to enter the while loop, this condition, whatever that condition is, must be true in order for you to enter the while loop. So if one of these conditions that is related to the condition of the while loop is not met, then your while loop should not execute. So that is the way in which rigor is applied. Now one of the notations, formal notation we use mathematically is that of Z notation. And there are a number of them in use. There is Z, there is VDM, there is B, there is OCL, there are Petrenet, colored Petrenet, all those of them. And again, it's just like having multiple programming languages, and you select the one that's most appropriate for the area, the problem, space that you're working in. This is one particular notation that I've worked in extensively, and we use it to then describe the system in mathematical terminology. The thing with the graphical models is that they're not very precise. They allow for flexibility in use, and so they allow for multiple interpretation of how a system may be designed. And that can lead to problems. Because if we can interpret one thing multiple ways, then it means that someone may interpret it incorrectly. With the use of formal specification now, we ensure that things are precise. It's mathematically, that's be mathematically correct. So the mathematical notation cannot be used in developing code. The graphical notation can be used and is used for developing code. And so what we do in applying formal specification is we transform the graphical notation into a mathematical representation. We then analyze this mathematical representation to find out if there's anything incorrect in the design. And then if we identify something incorrect, then we feed it back and correct the graphical model. And we stay in that, we iterate through that sequence of activity, design graphical, transform to formal, analyze formal, feedback error correction, modify the graphical, transform back to formal, and we go through that iteration until we are satisfied that there's a level of acceptability in the correctness of it. Now, one of the accidents, again, another system failure that I just have a couple of minutes to talk about, that is the Lion Air crash. And there was also a similar accident with the Ethiopian airline, wherein Boeing has developed a new commercial jet, the 737 MAX, and because of its new design, they changed certain physical features of the aircraft, resulting in it falling into an unstable flight configuration. And so to address that, they developed software to correct this design anomaly. Right? The problem is that there are multiple, again, aircrafts don't fail because of single points of failure. It's usually a cascading series of things. And so with Lion Air, it was the fact that they had written software to correct something, and that software analysis effort was not thorough. It was not rigorous. Had it been rigorous, then they would have been able to identify some things that were not being met in this system operation. And so I just speak of the Lion Air one here. There's an Ethiopian crash as well, which is very similar because of the same software system. It was known as MCAS, which is a new system that they installed. And the verification process that would have been done for DO-178C compliance was not done the way it should have been done, and this was one of the reasons why failure occurred. But this flight was, this is a flight intended flight part from taking off from this airport in Jakarta, Indonesia, and flying over to this island, Pangkai, Penang, and it didn't make it. Now, so they were able to get the black box and they were able to analyze the data on it and determine that in this graph here, this is the altitude of the aircraft that crashed. The thin red line is the altitude that it's supposed to travel along, its altitude climb from ground level up to 18,000 feet in normal operation. Right? But what happened to the flight that crashed was the heavy red line that you see here. And so what happened is that this system, the MCAS system, simply, when it detected that the aircraft was flying at too steep, what they call an angle of attack, the angle at which the aircraft is climbing, it takes control of the aircraft from the operators, from the pilot, and turn the nose down. And so this happened at this point. This was the first. So they took off and they were climbing up. The system detected that the aircraft was climbing too steeply by the parameters programmed into it, and so it took control and tried to turn the nose down. The pilot struggled and took control back and put it back up in a climb, and this went on for nearly 11 minutes. The time on the bottom here tells you the time. It was recorded that struggle with the pilot and that MCAS system, where the MCAS system took control, the pilot took back control. The MCAS system took control, pilot took back control, occurred 24 times. Eventually, it nosed down, and the pilot was not able to regain flight, lost lift on the wings, went into a stall, And because of the low altitude, the pilot was not able to recover from the stall, and it crashed. Now, this other graph shows you the speed of the aircraft with respect to the same time frame. And at takeoff, so it should have taken off at a lower speed here than it actually did, and it would have transitioned to various speed level. But what was happening with the MCAS thing was that its speed was fluctuating, and it didn't attain the speed for cruise flight, get up to cruise altitude as it should have. And then at the point where it lost lift and then nose down, you saw the speed just peaked up. And that's a crash. Now, and so this is I put the two graphs together so you can see them clearly. Now, part of the problem with that MCAS system there, though, was that in doing this formal specification is a key feature to it. It forces you to ask questions about the system that you normally would not think about if you were just developing the code, or if you weren't doing formal specification, formal methods application. One of the simple thing that formal method does is that it requires every user-defined, I'm going to use the word variable. You have to, every variable you declare in your program, formal specification requires you to specify its type, to specify its range of values, and to specify the operations that can be applied on this particular type. And so, when we're using formal specification, if you're not using formal specification, you go on, you write your code, and you might be doing something like airspeed, for instance, is one of the things recorded here. You would never think about asking the stakeholder, the pilot, so what's the airspeed that this MCAS system should be operating at? Is there a range of values where MCAS can work? Is there a range of values where MCAS should not be working? And the same thing, it would force you to ask a question about the altitude, because these are two properties of an aircraft that is critical in every avionics system. Critical avionics system. The aircraft's altitude, speed, heading, just those three properties are critical information. And in developing a system, formal specification say you have to know everything about these properties. You have to tell me, that's a formal specification methodology. It says you have to tell me what's the type of these variables, what's the range of these variables, and what are the operators I can apply to these variables. And one of the things that formal specification now do is force you that you can't combine things that are not to be combined. Some of you may have programming, say, the C programming language, and you know that you can multiply, you can carry out arithmetic operation on things that are not arithmetic operands. So I can multiply an integer by a character value by casting it, and programming language allow me to do that. Formal specification say no, you can't do anything of that nature. If I have specified a type and I specified operands that work with that type, those are the only things that can go together. Those operators and that particular type. I cannot bring another type in and use that operator on it. And so one of the things that would have occurred in doing an MCAS development, that somebody, as the formal specification developer, would have gone back to the stakeholders, whether the engineers or the pilots, and say, at what altitude does MCAS start working at, or can start operating at? And definitely, you would never want a software system to take over control of an aircraft at what looks like 2,000 feet here and turn its nose down at 2,000 feet. Because there's not enough altitude that should it lose lift, there's not enough altitude for the pilot to regain lift on the wings and maintain control flight. And similarly with the speed. So formal specification would say you got to find out what speed is it safe to have MCAS, the system, operating at. And so immediately you would have recognized that we don't want MCAS to be operating at this altitude. MCAS maybe said we don't want it to operate below 8,000 feet, because 8,000 feet is a magic number in terms of pressurization of the aircraft. So that might be a safe number. And for instance, the speed, it might say, you know what, we don't want it to start operating until the aircraft has achieved a certain speed, wherein it doesn't have to depend on extra flaps to maintain lift. Right? And so we would have seen that doesn't work. As I said, one of the other areas in which avionics has become a critical place that in drone, remote drone operation, unmanned aerial vehicles, and since these crafts are operating, some of them operate autonomously, and so they fly without remote control because of the type of work that they are, payload, the work effort that they're supposed to be carrying out, and that is critical. So, as I said, I've done quite a bit of work in this area. Some years ago, at the University of North Dakota, I worked on a UAS project, which is a risk mitigating project. And so, what the university was asked to develop a system in which drones could operate in that environment, in the national airspace, without restriction, without being in a restricted airspace. Today, if you want to test fly or carry out operation with unmanned aerial vehicles in the national airspace that is airspace controlled, owned and operated by the U.S. Aviation Authority, the FAA, then you have to request permission, and what they do is that they carve out an area in space where they said, okay, you can operate within these coordinates up to this altitude. And then they have to have an air traffic controller specifically watching that area in order to ensure that no other aircraft enter that area while they are operating your drone. And it's a very expensive effort because they have to divert commercial traffic around this area. And so they asked us to see if we can come up with a system that will be able to provide some situational awareness to the operators of these drones so that they will be aware of what we call a risk level in that space. And if that risk level is about to be exceeded, then we ask the operators to take some action. The idea is that we're not going to tell them what to do, but they will have to take some action to reduce the risk level. And so we worked on that project. So we developed a display system, which my team reverse engineered that display system. And in reverse engineering it, we were able to identify that over 170, it's an object-oriented system, 174 classes, so the attributes, association, methods, and parameters. And then what we did was we applied formal specification to that system in order to meet DO 178C specification. And we were able to detect a number of errors that were in the system that were not detected during testing. But the formal specification identified a number of anomalies, like, for instance, mismatch types. Operations were being applied to two operands that were of different type. Now, while the code allowed the successful execution, formal specification said you should not do this because you cannot guarantee that every time that you do this, the particular values would result in correct information. And so that's one of the things that formal specification traps. We were also able to identify that there were some changes being made to values which could go out of bound, but the system would not have detected it. So then we identified some critical thing, and then this was feedback into the design of the system, and they attempted to carry out correction on those efforts. And so in closing off, what I say to you is that formal specification, while it's a very challenging, very specialized area of work, it is critical to the development of safety critical system. I should not be using the word critical twice in the same sentence. But without formal specification techniques, developing safety critical system is a risky business. The downside is that while they argue that it adds, opponents of safety critical techniques argue that it adds a lot of effort and time in developing a system. That may be true, but it reduces the amount of testing that has to be done on those systems because there are some things that we can show that it is mathematically correct. If we can show that a particular function is mathematically correct, then we don't need to test it. And this was the mantra that came from a researcher, a computer science researcher, expert in the area. It was a mathematician, Professor Dijkstra, had argued that if you can prove something to be mathematically correct, then you will never have to test it. Their testing cannot show more than what the mathematical proof has done. So that concludes my address. I hope that I provided some useful information to you. Unfortunately, I'm not there to take your question, but my email address is in the program, the conference program. You can reach out to me if you're interested in any aspect of anything I presented here. It has been my joy to communicate with you, to share what information you may require, and possibly end up maybe even working with some of you. Thank you very much. My timer went off here.
I guess it was a very sweet video of him telling about enlightening his audience here. So I will take this privilege to thank Manatol for in the meeting and for in the audience who patiently listen for these sessions. So thank you Manatol and thank you Professor Dr. Emmanuel Icerect for your sweet video all the way from USA. Thank you Manatol.
Thank you. ಮೈಕ್ ಇಲ್ಲ ಇದು ಮೈಕ್
ಏನದು
ಅದು ಆಫ್ ಮಾಡು ಮ್ಯೂಟ್ ಮಾಡು ಒಂದಿನ
Thank you one and all for being in this meeting. I guess it's the end of the event for today. We have valedictory event from 4 o'clock in the evening. We guess we'll meet there. Thank you one and all. Attendance sheet.